Finding the prime factors of a large number is traditionally a brute force search, but we can bypass that iterative process by translating the problem into a strictly defined algebraic mapping sequence. Every integer n can be universally expressed as 10k plus s, where s is an integer between 0 and 9. This provides a base coordinate system for any target number. If the target number n is composite, it can be defined as a specific function of two factors, which we denote as phi of p and q. This relationship allows us to isolate those factors, p and q, by solving for the integer roots of a derived quadratic equation. Factorization is no longer an open-ended counting exercise. It is a structured algebraic puzzle with a finite solution. A standard quadratic search faces a logistical hurdle. Without parameters, checking for integer roots across massive numbers remains computationally expensive. To make this approach viable, the algorithm applies absolute mathematical limits to the search space. These boundaries are deterministic, derived solely from the variables k and s extracted from the target number. This creates a finite zone of inquiry. We only compute values within this specific calculated range. If the algorithm tests the entire range without finding integer roots, it proves the original number is prime. The process begins with a parity check, classifying the target based on whether the hypothetical factors p and q are even or odd. The base variables are then used to calculate a new operational variable, t. This diagram constructs the quadratic polynomial, x squared minus 6r plus tx plus k minus r equals 0. In this formula, x represents the prime factors. We need to identify the specific value of r that produces whole integer solutions for x. This equation defines the relationship between the factors. Our task is to iterate the variable r until the solution is found. We focus the search on the core of the quadratic formula, the discriminant, denoted as delta of r. The formula for the discriminant is delta of r equals 36r squared plus or minus 4 times 3t plus or minus 1, r, plus t squared plus or minus k. A definitive requirement for integer roots is that delta of r must be a perfect square. This establishes a binary test. If any valid r produces a perfect square, n is composite. If no such r exists within the bounds, n is prime. The discriminant provides the conclusive evidence. The search for primality becomes a search for a square integer output. Testing every integer r from 0 up would be inefficient. The algorithm uses a more direct starting point. It identifies a median marker, r star, calculated directly from n and k. The search initializes at this median, moving outward in calculated increments to test surrounding values of r. This sequence is strictly limited. It stops once the search reaches the mathematical upper bound. Starting at the median avoids unnecessary computation, focusing only on the most probable search space. Let us apply this sequence to a known composite number, 10,001. The algorithm extracts the base variables. K0 is 333 and S0 is 3. It tests the discriminant on the first iteration, where R0 equals 1. The discriminant produces a perfect square, identifying the integer factors as 73 and 137. For composite numbers, the median initialization is so precise that the proof often appears in the first few steps. Establishing that a number is prime requires exhausting the space. Consider the target 1013. The algorithm sets the median anchor at 5,644 and the upper limit at 6,841. It executes 25 iterations. None are perfect squares, so each is rejected. Reaching the limit without a result concludes 1013 is a prime number. Exhausting the mathematical range is not a failure of the algorithm, it is a deterministic verification of primality. This method replaces the uncertainty of prime factorization with strictly bounded algebraic certainties. Establishing primality does not require an infinite search. It requires calculating the correct mathematical limits.